Good morning, everyone. Good morning. Welcome to Saturday Physics for Everyone this fall 2022. We're so glad to welcome you all here to our third lecture in our series. We've got two more after this. Today we've got Professor Alan Nathan doing the physics of baseball. A quick introduction of myself. My name is Irene Lyra Ansager, and I am the physics undergraduate coordinator of recruitment, research, and placement at the department. So I help our students with get into the undergraduate program in the physics department if you're interested in doing a physics major. And then with our undergraduate students, I also help them find research opportunities and other things that they'd like to do during their time in the physics department. I'd also like to thank our Society of Physics students who gave us some of the physics demos out in the lobby this morning. Really interesting things to learn about this morning. And finally, I'd like to introduce our professor, Alan Nathan. So Alan Nathan is the Professor Emeritus of Physics at the University of Illinois. He got his undergraduate degree at the University of Maryland and graduate degrees at Princeton. After a brief postdoc appointment, he joined the UIUC faculty in 1977, where he has been ever since. He had a long career doing experimental nuclear and particle physics, where he studied the collision of subatomic particles. Eventually, he transitioned into the physics of baseball, where he began by investigating a different type of collision, that between the bat and ball. He has written many articles on baseball, both for academic journals and online baseball publications. He has given numerous lectures to a variety of audiences, and he maintains an oft-visited website, baseball.physics.illinois.edu, that many people have found a useful resource. He is interviewed regularly by the media and has consulted for various organizations, including MLB, NCAA, USA Baseball, and several MLB clubs, as well as various technology companies. And he is a lifelong fan of the Boston Red Sox. Let's welcome Professor Alan Nathan.
Yeah, thank you, Irene. It's nice to be here. Having your cake and eating it too, what does that refer to? I had to explain it to my wife. She wasn't sure. I get to do this sort of stuff and call it actually doing work. What could be better than that? So this is a great time to be giving a talk on the physics of baseball because the postseason is well underway. Phillies won last night. They're up 2-1 on San Diego. Houston is up 2-0 against the Yankees. Well, as a Red Sox fan, you know what they always say. I always cheer for the Red Sox and whichever team is playing the Yankees. So anyway, both games, both AL and NL going on today. Okay, so let's go on. Let me first briefly tell you about my personal journey in this area. It began in this very room, way back in January of 1997, where this same series of talks I gave, here's the title, When Ash Meets Cowhide, and it involved reading this book, which had come out about 7 or 8 years earlier, and then giving a talk about it. And it was supposed to be sort of a one and done kind of thing, never to be returned to again, but there was a News Gazette reporter who was in the audience, and he interviewed me afterwards and wrote it up in the paper the next day, and there it is. And there I am in a much younger state where my hair was dark. And basically, everything took off from there. Okay, so thank you, News Gazette. So some references. This is the book that I read. This is the third and the first one was, the earlier one was the first edition. This is the third and final edition. Bob Adair is a physicist, or was a physicist at Yale, passed away a couple of years ago. And he was sort of my mentor in this. He has a couple of very interesting quotes from the book. Our goal is not to reform the game, but to understand it. And that, you could apply that to many different things that physicists do. We're really sort of curiosity driven. We're trying to understand the game, not change the game. The physicist's model of the game must fit the game. So, this is the physics of everyday life where simple textbook kinds of things are kind of difficult to apply, okay? And so you have to create a model, and the model is constrained by the laws of physics, okay? But it's also constrained by observations from the game itself. The game itself is like the big laboratory, okay? And whatever model you create to describe what's going on, it better fit the game, okay? And that sounds obvious, but there are lots of examples of people who create models where you wonder, have they ever actually watched the baseball game before? Okay, anyway. And here, for those of you who are interested in baseball analytics, which is kind of running rampant these days in baseball, at every level, the Illini are doing this, for example. This is a great resource, analyzing baseball data with R. R is a software code, okay? And this sort of the code that R and Python together are what people in the industry itself, in Major League Baseball, are actually using. So I recommend that. And my website that Irene mentioned. Okay, so here are the topics I'm going to cover. And I'll explain the meaning of these things as we go along. Building a worse mousetrap, Rocky Mountain High, humidors, they're not just for cigars. And those of you who remember the TV show Laugh-In from the late 60s, order in the courtroom, here come the judge. Okay. All right, building a worse mousetrap. So I want to talk about the physics of the ball-bat collision. And here are a couple of videos here. This is a ball fired at a steel plate at 120 miles an hour, observed with high-speed video. And notice the ball getting crushed as it hits against that plate and bounces off. And this is actually a very recent photo from maybe a couple of weeks ago, 3 weeks ago. Giancarlo Stanton for the Yankees, boo. And you see the ball and the bat are in contact with each other. This is a rare photo of opportunity. And again, you see the ball being crushed, and you see the ball sort of wrapping itself around the cylindrical surface of the bat. One thing to note here is you could judge the speed coming in and notice that it's going a little bit slower, actually quite a bit slower on the way out. It's going at about half the speed on the way out as on the way in. And what does that mean? That means a lot of energy is lost. It's a very, very inefficient collision. And that plays a role in the ball-bat, a major role in the ball-bat collision. So more on that in a second. Okay, so despite this violence of this collision, some basic laws still apply. One of the laws is conservation of momentum. So, and the way that, imagine firing a shotgun, there's a recoil. Well, there's a recoil when ball hits bat. Notice that bat recoiling backwards. Now, if the bat is already moving, as when you're swinging the bat, there's not enough recoil to make it actually go backwards, but it does slow down considerably, and you can see that in this picture here, in this video here. Each of these dots represents an image, okay, separated by a certain amount of time, and notice the images are getting closer together after the collision, meaning the bat is moving a lot slower. And this is necessary. This is a necessary consequence of conservation of momentum. Ain't nothing you can do to stop it from happening, okay? Okay, now, let me get to the heart of the matter. One of the primary things that batters are interested in is what nowadays is called exit velocities. You watch a game on TV, they talk about exit velocity. And whether you're trying to hit a home run or punch a line drive through the infield or even a ground ball through the infield, your chances of getting on base by and large are better the higher the exit velocity. I mean, for a home run, it's pretty obvious. You want that ball to travel a long way. But even for a line drive, you want that ball to get through before the fielder can catch up with it. So what determines exit velocity? What parameters of the collision? And there are 3 overall parameters, and this is the only formula you're going to see in this talk, okay? And one of the great things about that Adair book, the one I first read, is there's barely any formulas in that. There's a lot of wisdom in it, but very few formulas. You don't need formulas. But this is a useful one. Pitch speed, bat speed, and something called the collision efficiency. So exit velocity equals the collision efficiency times the pitch speed plus 1 plus the collision efficiency times the bat speed. So notice that 1 there. So these are typical numbers for a let's say a 34-inch, 32-ounce bat, okay? This Q, this collision efficiency is about 0.2, meaning it's not a very efficient collision, okay? And I'll tell you why it's not efficient in a second. But if the ball were a super ball, okay, which is incredibly bouncy, okay, here's my super ball, you know, compared with bouncing a baseball, okay? That 0.2 would be more like 0.5 or 0.6. It would be a lot different. So you can plug numbers in here, and you can see that with a pitch released at in the mid-90s of miles an hour, by the time it crosses home plate, it's going a bit slower. It's more like 85 miles an hour. And a 70 mile per hour, which might be a typical bat speed, that plug into there and you get 101 miles per hour, which if the ball takes off at the right angle, will travel a bit, around 400 feet or so. That's sort of the standard 400-foot home run. Now, the interesting thing to note is that 1 plus Q, 1.2, is much bigger than 0.2, meaning the bat speed matters much more than the pitch speed in determining the batted ball speed, the exit velocity. Okay? And, basically this is sort of something you knew already in the following sense. You could hit a ball off a tee, okay, where the pitch speed is 0, and you could hit it a long ways, or a fungo. You just throw it up and hit it. And now try bunting the ball. In that case, the bat speed is 0, and the ball's not going to go very far. Okay, so you sort of knew this already, although you may not have known it quantitatively, you certainly qualitatively already knew it. Okay, so the thing I want to talk about now is this factor Q here. Why is it so small? And it depends on 2 different properties of the ball-bat collision. One is the weight, and actually it's sort of the weight distribution of the bat. It's sort of the amount of weight in the barrel of, in the business end of the bat. And that determines the recoil. Something light will recoil more than something heavy, okay? And when it recoils more, that's energy that's transferred to the bat that didn't go back into the ball, so it reduces that collision efficiency. So heavier is better in terms of what happens with Q, but, and there's a big but here, you have to swing the bat also. So usually when the bat is heavier, the bat speed is going to be less. And so you could see there's going to be some optimization that goes on, where there is some optimum bat weight that optimizes the product basically of Q times the bat speed. But that's not the part that interests me most. The part that interests me most is the bounciness of the ball, the thing we were just talking about. And that has, I like to call it bounciness, but it has a technical name. It's called the coefficient of restitution. It's a number between 0 and 1 that characterizes how high the ball bounces, okay? So a super ball has a coefficient of restitution of about 1. And if I took a clay ball, something made out of clay, and just dropped it, it would just hit and not bounce. It would have a coefficient of restitution of 0. And the baseball is sort of halfway in between. It's about 0.5. So higher coefficient of restitution means a larger collision efficiency and therefore greater exit velocity. Now, there's an important point. It matters what the ball is bouncing from, okay? The bat matters also in this coefficient of restitution. In fact, it's given the name ball-bat coefficient of restitution, okay? All right, so the topic I really want to talk about is why is an aluminum bat better than a wood bat? Now, aluminum bat is very different, okay? Here's an aluminum bat, it's a fairly old one. And an aluminum bat is hollow, okay? And so that means that for a given total weight of the bat, a smaller fraction of the weight of the bat is in the barrel because this is a very thin aluminum shell compared with a wood bat. So that would tend to make the collision efficiency higher, but again, the less weight in the barrel would make the collision efficiency lower, but you could swing it faster, and to a large extent, it's sort of a net wash. That's not why aluminum is better. The reason why aluminum is better is the so-called trampoline effect, and that's what I want to talk about now. So, pretend that this is a bat, and here's my hollow bat, and when the ball, hits this aluminum bat, the wall of that bat can compress. So you're seeing it in this picture here. This is the ball hitting a wood bat, a solid wood bat, and you see it compressing in this little cartoony picture here. And now the ball is hitting a hollow bat, and the hollow bat compresses so that some of the energy is taken up not by compressing the ball, but by compressing the bat. Now, the ball is very, very inefficient. The reason why the coefficient of restitution is so low is that if you were to cut open a baseball, you would see it's mostly yarn, wool yarn. So as you compress that ball, fibers of yarn are rubbing against each other, creating a lot of heat, and that heat represents energy that's lost, energy that's lost to the kinetic energy of the ball. But less so when impacting a hollow bat because some of the initial energy is taken up by compressing the wall of the bat, and for reasons which I won't go into, that energy springs back again and is given back to the ball. It's sort of like jumping on a trampoline, that's why it's called a trampoline effect, versus jumping on the floor. The floor has no bounce, but the trampoline does. And I have a little, so less energy dissipation, the ball bat coefficient is therefore larger, and therefore you get larger exit velocity. And left unregulated, aluminum bats, and now they're using composite materials. Again, they're still hollow, so you still have the same effect. Left unregulated, they would vastly outperform wood bats, okay? It's not even close. But they are regulated. Yes, question? I'm going to show you. Here's a little video I made during COVID. I'm going to first bounce those balls off of a hard surface. The hard surface is being with that. Okay? So let's take a look. This is a happy ball. It bounces pretty much like a super. Okay? Very well. Here is the sad ball. Boom. It hits to an immediate ball. Okay? Happy ball, sad. Okay? So when I bounce it off of a wood bat, behaves one like a super ball, one is totally dead. Okay, now I'm going to instead bounce it off a very flexible surface. The ideal bat. This is the so-called bongo paddle. Okay. It is a plastic paddle with a thin plastic membrane that's very, very flexible. So now take a look. Here are the same two balls. I'm just going to drop each one. Here's one. And here's the other. And they bounce pretty much the same, and that is the trampoline effect essentially on steroids. Okay, so yeah, so the ideal bat in terms of exit velocity, where the wall is so thin that virtually all the energy that the ball initially had is absorbed into compressing that wall and returned back to the ball again. And this trampoline effect is not limited to baseball bats. You see it in golf drivers, which are hollow, okay, with a thin plate that compresses, and you get a trampoline effect. Tennis rackets, it's the strings of the tennis racket that do the compressing, that give you the trampoline effect, and maybe other sports also. Okay, so this ball bat coefficient of restitution is pretty much the same for all wood bats. there was an article actually just a couple of days ago in the New York Times about how ash bats are no longer being used because it's hard to find ash anymore. And they're using principally maple and to some extent beech woods. And there was a claim in there that I think is simply not right, that somehow maple bats outperform ash bats. And that doesn't agree with data that you can take at all, no, even from my way of thinking with common sense. Basically, all wood bats, when hit at the sweet spot of the bat, perform pretty much alike. But for aluminum bats, the ball bat coefficient could be substantially greater depending on the thickness of the wall, and a lot of technology goes into developing walls of the bat that are thinner and thinner, giving you more and more of a trampoline effect without denting the bat. You don't want to do that. So leading to more home runs. So here's NCAA home run trends from 1970 to 2010. And I'll show you what happened later in a second. But aluminum bats were introduced in the early 70s. Home runs per game rose. Then they imposed the -3 rule. I won't go into it, those of you who may know, okay? And then it decreased, and then it started to increase again when batters became used to that. And they had a new standard called the BESR, Ball Exit Speed Ratio Standard. That sort of worked for a while. And then composite bats were introduced in the late 2000s, okay, 2008 or 9, and things started to rise again. So NCAA, their committee that I was on, recommended coming up with another method of regulating the performance of bats. And basically the idea is to regulate this quantity that I've told you about, the ball bat coefficient of restitution. Because that turns out to be, and this was sort of the key insight, a very useful surrogate for exit velocity. So if you want to regulate exit velocity, it suffices to regulate this ball bat coefficient of restitution. So it's a surrogate for performance, and it can be measured in the lab. So you can measure it in the lab. You could set a certain limit. You say, thou shalt not exceed 0.5, which is the actual number the NCAA is using, and high schools are also using. And so, which is just slightly better than the BB core for a wood bat. And this standard began in 2011, and here's a little video clip showing you how to measure it. You fire a ball out of a high-speed cannon on a bat that's initially at rest. It recoils. You measure the speed of the ball coming in and going back out. The bat recoils, and you take the ratio of outspeed to inspeed and do a little algebra, and you get the ball bat coefficient of restitution. So we know how to measure that very, very well. And so we know how to regulate the bats, basically very, very well. And what's the result? Beginning in 2011, there's a number here, the home runs per game in Division I NCAA baseball dropped by about a factor of 2. Great. This is sort of what we predicted. Physics really does work. But not everyone was happy with this, okay? Some teams were, some colleges were, some weren't. So NCAA decided to do something a little different to get back some of those home runs. They already messed with the bat, so they decided, let's instead mess with the ball. So what did they do? So this is neat. The previous NCAA baseball in that era had raised seams on it, okay? In fact, and this is a Major League Baseball, and you don't have to look at it. You could just feel that the seams are very, very different. Here, you want to catch it? And the other one. Whoops. All right, just pass it around. You can feel they're very, very different. And the raised seam ball does not carry as well. There's greater air drag on that ball. So that sort of, you could do a laboratory experiment, and this is what was done. Here is the NCAA raised seam ball fired out of a cannon at these parameters. And there's about a 20-foot difference between a flat seam ball and a raised seam ball. 20 feet is enormous. So beginning whatever year that was, 2015 or so, NCAA switched to that, and this is what happened. Home runs went back up again. But now everyone seems to be happy. They found a good compromise between this and this. So physics really does work. End of topic, on to the next topic. Yes?
So
I'll get on. We can talk about that afterwards. Ask me the question after I'm done. It's a long story. Okay, I want to talk now about the flight of the baseball. So, you know, from introductory physics courses, we know that when you have an object in flight, the forces determine what, the initial conditions and the forces determine what happens to that ball. And so what are the forces? Well, there is, gravity is always pulling the, so here's a ball flying along this direction here, and it's spinning with backspin, okay? Gravity pulls the ball down, okay, we know that. But there's also air drag. The ball, as it goes through the air, actually has to push those air molecules out of the way. That's known as drag, and it slows the ball down, okay? By a tremendous amount, by the way. And then there is the Magnus force, which is the force on a spinning baseball that makes the baseball swerve, okay? That's the, yeah, and by the way, this little picture applies whether you're talking about pitch balls or batted balls or even thrown balls, okay? It's, the physics is all the same. Details might be different. Let's see. Oh yeah, drag depends on properties of the atmosphere, such as the air density. So why the air density? Well, the greater the air density, which happens in cold weather, it's lower air density at sea level than it is at higher elevation and other things. The greater the density is, the more air molecules you got to push out of the way, so the more drag there is. Also depends on a property of the ball known as the drag coefficient. I won't go into that too much, but it has to do with how aerodynamic the ball is. And the seams play a big role, okay? In fact, you just saw from that little NCAA thing how big a role the seams play. So effective drag and so how does a real life baseball differ from what I like to call a physics 101 baseball? A physics 101 baseball experiences only the force of gravity because it's too complicated for an introductory course to treat those other forces. At least it was when I was teaching. So this is a famous home run. This is the home run hit in August of 2007, I think, when Barry Bonds hit the home run, his 756 career home run that broke the career home run record of Hank Aaron. And this is the actual trajectory of the ball that you get from ball tracking technologies. The ball actually, it never actually went 430 feet because it hit something else before that. But if you extrapolate that trajectory, that's what where it would have ended up. And this line is sort of a model that I created with the actual forces, the drag and the lift forces from the Magnus force, which very nicely reproduces the actual trajectory. Once you have a little computer model like that, then you can start playing games. And so the first game I played was, all right, I know the initial conditions. Let me now turn off the drag in my computer and see how far the ball would have gone. That's the dash line. It would have gone nearly 700 feet. So you can see in the real life situation of baseball, when you say neglecting drag, that's not a very good approximation. Now, if you also neglect the lift you get from the backspin, from the Magnus force on the ball, you include the drag but neglect the lift, you see that has an effect too, but it's nowhere near as great. Drag matters a lot. The Magnus force also matters, but not nearly as much. Okay. So StatCast, so those of you who watch MLB games on TV regularly know about StatCast. It's a camera-based, it uses so-called Hawkeye cameras. It's a camera-based tracking system for tracking virtually everything on the field. It gives you the full trajectory of pitched balls, batted balls, and thrown baseballs for that matter. It gives you the spin rate and the spin axis. So, I mean, if you're a physicist, it gives you absolutely everything you need in order to, you know, try to pin down what those trajectories should look like. It gives you tells you where the players on the field are and how they're moving. That's pretty interesting. In the future, it's going to give you the trajectory of the bat, motion of the batter. This is sort of all biomechanics stuff, motion of the pitcher. It's sort of working to do that. It doesn't do that yet. Unfortunately, not all of the data that StatCast measures is made available publicly, but I oftentimes can get the data just by being nice to people, and they're nice to me. And so I've done quite well that way. But if you're a physicist, okay, this is just an incredible body of data. I mean, think of all the thousands of pitch balls in a season and thousands of batted balls. Anyway, all right, so physics 101 versus reality. So this is the Rocky Mountain High part of the thing. Distance, so for a baseball that's hit sort of in the, well, let's look over here first. Here is a ball that's hit in the range 101 to 105 miles an hour. These are sort of average values. This shows you that the distance, which is about 400 feet at this maximum, peaks at about somewhere between 25 and 30 degrees. In physics 101, it peaks at 45 degrees, so it's very, very different. The drag plays an enormous role in reducing that. And this is everywhere but Denver, and this is Denver, and you see the Denver effect is enormous. Okay, Denver's a mile high above sea level. Most of the rest of the major league stadiums are close to sea level. I guess Atlanta maybe is 1,000 feet, but this is over 5,000 feet, so it plays a big role. So the optimum launch angle is 28 degrees, not 45 degrees. Distance depends more or less linearly on exit velocity at a rate of about 5 foot per mile per hour. So again, if you took physics 101, it would not depend linearly, it would depend quadratically on exit velocity. And the reason why it's not sort of knocked down to be linear is because the drag actually also increases quadratically. So those two things play against each other and you get sort of a linear thing here. And again, you see Denver, this is everywhere else, this is sea level and this is Denver. The Denver effect is huge. All right, what have we learned? So I'm just going to go over these things quickly. As I already said, a 1 mile per hour increase in exit velocity will give you an additional 5 or 6 feet, okay? And that increases your probability of hitting a home run, assuming you're hitting it at the optimum angle, of about 15%. Temperature, a 10 degrees change in temperature. If you increase the temperature, you're reducing the air density, you're therefore reducing the drag, and you're increasing the distance, okay? You get an additional 3.3 feet for 10 degrees, which increases your probability of a home run by about 10%. And altitude, you get about 6 feet per 1,000 feet. And, okay. What else have we learned? Assuming no wind, this is an interesting one, and I won't go into the details of why, but you could ask me afterwards if you like. Baseball, for a given exit velocity and launch angle, balls hit towards center field actually carry better than balls hit pulled or opposite field, okay? And, you think about it, that's probably why the center field fence is further away than down the foul line. Here's a really interesting one. 5 miles an hour of wind, either outblowing or incoming wind, changes the distance by something like 18 feet. That's enormous. 5 miles an hour is barely perceptible, right? It plays a big role, and it's the hardest thing to take into account because we don't have accurate measures, either in time or in space, meaning the wind speed and direction can change throughout a ball game. And it could be different in different parts of the ballpark. You probably can see, you look at the flags over here and they're blowing in one way and back there they're blowing another way, okay? So it's very hard to take that into account. And let me skip this. All right, so I wanted to give you that quick introduction to baseball aerodynamics. Let me move on to the next topic. This is kind of fun. Humidors, they're not just for cigars. So this is the humidor at Coors Field in Denver. That's the first place they started using a humidor in 1995. Does anyone know who this guy is? Somebody must know, besides me. El Tiante, Louis Tiant. Okay, he's smoking a cigar. All right, so I want to tell you a little story. This is kind of fun. Back in September 2010, this article appeared in the Arizona Republic. Arizona Diamondbacks Chase Field could become pitcher's haven with humidor. Okay? Shortly thereafter, I published a paper with my collaborators and wrote an article on Baseball Prospectus in which I talked about, we anticipated that they might put a humidor in at Chase Field. You know, in Arizona, it's very, very dry. And I'll tell you in a second how that affects the ball. But we predicted a 37% reduction in home runs would occur if at Chase Field they had a humidor. And I talked with this guy, Nick, and I told him about it. And then finally, Arizona Diamondbacks back off the idea of using a humidor this year. And I like to think there's some cause and effect here. And actually, I think there really was. It was because of this predicted big reduction that they decided against it. They wanted to study the matter a little further. And this went on and on. In 2017, get a grip, Arizona Diamondbacks to install humidor at Chase Field. The humidor at Chase Field, what's up with that? That's an article I wrote. You notice the dates, this here, and okay, just a couple of weeks later. Impact of humidor at Chase Fields could be significant. This is yet another week later. Arizona Diamondbacks Chase Field humidor pack pushed back to 2018. So history repeats itself. And finally, in 2018, they unveiled their humidor. Okay, they did their own calculations and decided that they should do it. All right, so I want to go through kind of, you get some insight as to how a physicist thinks about these things. So let me tell you about this. So let me first talk about the effect of humidity on the properties of a baseball. So humid air makes the ball less bouncy, okay? It absorbs water and it doesn't bounce as well. This so-called coefficient of restitution, the COR, decreases, which means the ball isn't hit as hard. Lower exit, all other things equal, lower exit velocity. It also makes the ball heavier. You absorb water, it becomes heavier. Once again, that means the ball isn't hit as hard, okay? You can transfer more energy to a lighter ball than you can to a heavier ball. But the ball carries better. A lighter ball will, all other things equal, will carry better than a heavier ball. So you could take a baseball and compare it with like a styrofoam ball of the same size, styrofoam being, and you know that styrofoam ball is not going to carry very far. And then humid air makes the ball larger. That's actually a very, very small effect. So the ball doesn't carry as well because of that too, but we can ignore that effect. But the two big effects are the coefficient of restitution and the weight of the ball. Okay, so these effects can be measured in the laboratory. And so that's what, well, okay. So here's the plan of attack for trying to study this problem. Use laboratory measurements to determine the effect of humidity on both the bounciness and the weight of the ball. Use the physics of the ball-back collision to predict how those changes to the ball will affect the exit velocity, the batted ball speed. Use the physics of baseball trajectories to predict how those changes would then affect the trajectory of the ball, the fly ball distance, okay, which now changes both due to the fact that the exit velocity has changed and the weight has changed. And then use statistical data from StatCast to estimate how that change of distance would affect home run production. So that's the sort of what the plan is. And the first step in the plan is, it's all discussed in this paper here, weight versus humidity, coefficient of restitution versus humidity. And so this is 70 degrees relative humidity between 0 and 1, 0 and 1. Here is the weight. And so in going through this calculation, the humidor is set at 70 degrees, 50% relative humidity. It was assumed that left untouched, the balls just out in the open would be at about 20% relative humidity, which is, in Arizona, is very, very dry. So we wanted to figure out the effect of going from a 20% relative humidity to 50%, both with the weight, you see the weight increases, and the coefficient of restitution. Here's 20%, here's 50%. Okay, you see the coefficient of restitution went down. So this is the assumptions. The weight increased by about 3.7%. The COR decreased by about 4.6%. The change in the size of the ball, as I told you before, was totally negligible. So the result, there was a 4 mile per hour decrease in exit velocity. It went from, say, 100 miles an hour to 96 miles an hour. Of that, 2/3 of that reduction came from the COR, the bounciness. 1/3 of the reduction came from the weight, the higher weight. There was a total of 14 feet decrease in distance of a fly ball, again, on a typical home run trajectory. 20 feet of that is due to the exit velocity being lower, but the carry is a little bit better, so you get back another 6 feet. So minus 20 plus 6 is a 14-foot decrease. And that gives you a 35% reduction in home runs. Okay, so that's the prediction. Confronting reality. This is what 35% reduction, and there is some uncertainty on that. I mean, the model is, it's a model, right? And I'm estimating plus or minus 10% here, but it's probably a little bit better than that. Now let's take a look at the data. So here's the data. So 2015 to 17, I looked at all the Arizona Diamondback hitters, okay, playing away games, home runs, playing home games. And then the humidor was installed, so 2018 and 19, and it was after the 2019 season that I did this calculation, the Diamondback hitters hit essentially the same number of home runs away. So that's my control group, but only hit this many home runs at home. So you see there's a big decrease, okay? And that decrease is 32%. And so here it is, predicted, actual. One could argue the little model that I created maybe worked better than it had a right to, given that there's some uncertainty on that. But, home runs, the message is not so much what the numbers are. There was a substantial decrease in home runs in Chase Field, and the prediction and the actual decrease are amazingly similar. Physics rocks. Okay. All right. Oh, and by the way, there's a postscript to this story. So in 1995 is when Coors Field had their humidor. In 2018, it was Chase Field added to that. By 2021, there were a total of 10 major league stadiums that had humidors, and beginning this current season, all 30 MLB stadiums store their baseballs in a humidor. Now, I haven't gone through an analysis of all of the 30 of these, but the goal of doing that was to produce less variation in ball properties, both with location, okay, and with the season. So as you might imagine, if the balls were just stored out in the open in the spring and the fall when it's relatively dry, the properties would be different than in the middle of the summer than when it's very humid. That's especially true in places like Miami and okay. But anyway, and so I think that goal was quite nicely achieved. Okay, order in the courtroom, here comes the judge. So I want to talk about home runs in Major League Baseball and how they've changed over the last bunch of years. So what I'm plotting is in-play home run rate. So the number of home runs per ball hit in play. It's a number like, 3, 4, 5%-ish, okay? And 2013, 14, and beginning in 2015, it began to climb, okay, reaching a maximum at 2017. Then there was a decrease, and then it went back up again. So the all-time highest number of home runs per batted ball, and actually total numbers of home runs, since the number of batted balls are virtually the same in every year, except for 2020 when there was a shortened season. It began, this is the all-time highest number of home runs. A record was set. But since 2019, there's been a decrease, a significant decrease in about a 20% decrease. There was a 70% increase going from here to here, and about a 20% decrease since then. And the question is why? So MLB put together a committee and to try to discover why. And I'm going to give you a little bit of sort of analysis to show you what kind of things we learn. So why all the changes? So let's talk about what it takes to hit a home run. Conspiracy theorists like to talk about the ball being juiced, that Major League Baseball, there's some nefarious plan with Major League Baseball to increase the number of home runs and then decrease them again because people are against it. And all right, I doubt very seriously that ever happened. But one of the theories was that the ball is juiced or deadened, which is the opposite of juiced. And the traditional definition of juiced means that the coefficient of restitution is higher, or deadened meaning lower, okay? So a higher COR would mean a higher exit velocity, lower COR would mean a lower exit velocity, all other things equal. Now, you can do very careful tests in the laboratory, sampling tests. You're not going to test every single ball. You wouldn't have any balls left to use, but you do sampling. And you can measure these things in the lab, and they have been measured. And virtually every property of the baseball that affects the ball-bat collision has stayed pretty rock steady over the last dozen years or so, okay? In particular, the coefficient of restitution has stayed very steady, the weight of the ball, the size of the ball. It's stayed very, very steady. There's one part that hasn't stayed steady, and I'll get to that in a second. So Rawlings manufactures the baseball in Costa Rica. When I gave a talk here 3 years ago, I showed you little video clips from my trip to Costa Rica. It's an interesting process. And they go to a lot of effort. They really know very, very well how to control these various properties of the ball, the coefficient of restitution, the weight, the size. So you can rule that out. So what about changes in batter behavior? You're getting more home runs simply because batters are swinging harder to get a higher exit velocity, okay, which will give you more home runs. People really pay attention to this, are adjusting the swing to get a more optimum launch angle to give you home runs. Remember, if you hit the ball hard at 10-degree launch angle, you may get on base, you probably will get on base, but you're not gonna hit a home run with that low launch angle. You need to be above 20 degrees, below maybe 35 or 40 degrees, okay? And batters can control that with the way they swing the bat. So they even call it the launch angle revolution. One possible reason for the increase in home runs is that batters are trying to hit more home runs by adjusting that launch angle. And as an aside, some of that may very well have to do with the extreme shifting that's going on now that won't be going on next year because of a rule change. So if you're a left-handed batter, there are 3 infielders on the right side of the infield, one of whom is playing out onto the outfield grass, so that what might have been a line drive single in the past is just a hard out, okay? And so if you take away the line drive, okay, as a way of getting on base, what's left? You might as well try for the home run. And of course, there's the financial rewards for that also. So as I will show you, change in batter behavior, different launch angles, exit velocities, accounts for some, but by no means all, not even the majority of the changes. Change in the carry of the ball. In fact, this is the primary thing. Reduced air drag carries the ball further, and again, you could do laboratory experiments, you could look at StatCast data, and you can more or less figure all this out, and I'll show you how we do that in a second. And that really does account for most of the changes. Now, a fair question to ask is, why does the ball carry better? It could be changes in atmospheric conditions, but it's sort of hard to believe that you're gonna get huge changes in atmospheric conditions, averaged over a 6-month period from one year to the next. And it probably has to do, I need another baseball here, let me grab one. The one feature of the ball that's really hard to control is the height of the seams of the ball. Now, somewhere up there you have those two baseballs, yeah, and those are extreme differences. And you see those extreme differences amounted to something like 20 feet of carry, which is huge, okay? But there are small, I mean, there could be smaller changes that are almost imperceptible to the touch, you know, a couple of millimeters, say a tenth of an inch, say, or something like that. That would be, you know, given that these stitches are sewn on the ball by hand, okay, you might imagine that there could be differences from one baseball to another, maybe even from one year to another, as the, you know, as small little changes in the manufacturing is done. But nevertheless, regardless of why the carry is different, it is a fact, and I'll show you, and that accounts for most of the changes we've seen in the last couple of years anyway. So let me go into this a little further. So I want to discuss with you then, again, approaching this sort of like a physicist, what is the analysis plan? I want to use 2019 as sort of my base, and I want to look at other years, principally years since then, compared with 2019. And actually what I really want to do initially anyway is I want to look at 2022 compared with 2019. So in 2019 you had the largest number of home runs as well as home runs per batted ball, and it's quite a bit lower, 20% lower, or maybe 30% lower in 2022. So what I want to do is I want to create a model based on the 2019 data that tells you the probability of a home run for a given exit velocity and launch angle. So you could imagine taking all the data from StatCast and dividing it into little squares of exit velocity and launch angle. And for each square, you've got a certain number of batted balls, you've got a certain number of home runs, you take the ratio of one to the other, that gives you the probability, okay? And you have to smooth the data a little bit, but okay. So when you do that, this is what you find. Here is sort of a heat map showing you the probability of a home run, white is highest, green is lowest, as a function of exit velocity and launch angle. And you can see that, and this black line is the contour of where the probability is equal to a half. So everything above this line has a probability greater than a half, below the line less than a half. And this is sort of what it looks like. You can see that the optimum angle is where this curve is minimum, and that's about 28 degrees or so, just like I said before. Okay, so that's the first part of the plan. So this is then the probability of a home run for a given exit velocity at launch angle in the 2019 season. Next, I want to apply this model to the actual exit velocity and launch angle for the 2022 season, okay? And when you do that, you then can predict how many home runs would have been hit in 2022 if the carry of the ball were the same in 2022 as it is in 2019, okay? So there you go. Here is the actual number of home runs per batted ball in 2019, and this is the prediction in 2022. So again, let's think about this. In effect, I'm using the same model, okay? This model, that I showed you on the previous slide, let me go back to the previous slide. This model can be used to predict the number of home runs if the ball carried the same in 2022 as it did in 2019. So this already takes into account the different launch angle and exit velocities, and you see this not very different, okay? It's very, very close, the prediction, okay? But now, okay, so conclusion, the launch parameters were equally favorable, or nearly equally favorable, for hitting a home run in 2019 as they were in 2022. And now let's compare with the predicted. So here is, again, 2019, the 2022 prediction based on the 2019 data, and this is the actual number. And you see there's a huge decrease, okay? So there is much larger air drag in 2022 compared with 2019, such that the home runs are reduced by something like 30%. And so that's the answer to the question, at least for 2022. You can do the same thing for the other years. So the blue dots are the actual home runs. The red dots are the predictions based on 2019. And in these years here, there wasn't too much of a difference between actual and predicted. But beginning in 2020, there was, there progressively more and more difference in effect due to more and more drag. Now you can independently verify this because we have a great way to measure drag on a baseball, because there are thousands and thousands and thousands of pitch baseballs. We have their trajectories. We know how much the ball slows down, and that directly determines the drag, and that's all consistent. Okay, here comes the judge. Aaron Judge. Okay, that's great. It had to be a Yankee, but all right. So Aaron Judge, that was his 62nd home run he hit a couple of weeks ago, breaking the American League record. Okay, the previous American League record was 61 home runs by Roger Maris in 1961, another Yankee. And before that, it was Babe Ruth in 1927, who hit 60. But since then, of course, in the National League, Mark McGwire hit 70 home runs in 1998, and Barry Bonds hit 73 in 2001. But those are in the National League. All right, now, it's an interesting question to speculate. The baseball did not carry as well in 2022 as it did in 2019. That's what we just saw. Could Aaron Judge have hit more home runs had he, had the drag conditions, maybe all due to the baseball, been the same as they were in 2019? So that's an exercise you can go through. You could numerically estimate that. And so that's what I did. But let's take a look first. So so what I'm doing is plotting each, so this is 2019 and this is 2022, and each dot represents a batted ball for Aaron Judge. And the ones down here were not home runs. The ones up here were home runs, and I'm plotting that as a function of the probability based on the 2019 model. And this red dashed line here is probability of a half, just for reference. And you see that pretty much everything below a half is not a home run, and everything above a half is a home run, okay? And since the model was based on the 2019 data, basically that's what you'd expect. But now look at 2022, okay, where the ball did not carry as well. There's a handful of what you might call lucky home runs where the probability was low, yet he still hit a home run. But look at the number of balls that he hit that would have been a home run in 2019 that were not a home run in 2022, okay? And so when you add it all up, so I'm talking about those, result, 75. So had the 2019 baseball been used, Aaron Judge would have hit 75 home runs. I mean, there's some, which would have been a new MLB record. There's some uncertainty on that because this whole thing is a statistical problem. But nevertheless, he would have hit, there's no question he would have hit a lot more home runs. So he hit a lot of home runs, many more home runs in 2022 than he hit in 2019, despite the fact that the ball was deader. So, he really had it going. Okay, so I've come to the end. I've given you lots of examples of how physics enters the game of baseball. This is only a small fraction that I've covered here. I love talking about this stuff, so feel free to contact me, follow me, send me an email, follow me on Twitter, go to my website. And that's me at the Red Sox fantasy camp from about a dozen years or so ago, so wearing number 9. Okay, thanks for your attention. Be happy to answer questions.
We've got about 15 minutes for questions. I'll bring you the microphone so we can all make sure that we can hear you. Yes.
So, in my life, of course, time passes, and playing baseball is not as easy as it used to be. So we get into this other game called softball, which has a different size ball and different pitch speed. So and of course, at the collegiate level, we have a wonderful women's softball team. How does the effect of the ball size and things like that affect the carry of the ball and such?
Yeah, good question. So, yeah, how does the size and the weight? So a softball has a circumference of, I believe, 12 inches. A baseball is more like 9 inches. And so so remember, the ball has to push the air out of the way, and the bigger the ball, the more air it has to push out of the way, so the greater the drag would be. The weight counteracts that to some extent. A baseball weighs about 5.1 ounces, something like that. A softball, 6.5 to 7 ounces. It's not so strongly regulated. But the heavier softball tends to counteract the effect of the larger size. But I think the larger size wins out, so there's greater drag. I don't remember the numbers off the top of my head. And I won't try to do it in real time here. But yeah, if you just compare the area, pi r squared, for divided by the weight, compare that for a baseball and a softball, and you could answer the question.
I would expect there also be a difference in the correlation, the restitution.
Yes, and yes. So and I don't remember, different softball leagues have different regulations. I think, let's see, the Amateur Softball Association, I think the coefficient of restitution is like 0.45, if I'm remembering right. Baseball is more like 0.5. So that's different. A softball can't be hit as hard. There's absolutely no question about that. And the weight really plays a big role there, okay? The coefficient of restitution plays some role, but the weight probably plays the biggest role. Oh.
Hello. Hello. So a lot of the studies shown today were on like the offensive side of the game. But have you done any studies on the pitching side of the game, such as like RPM with players like Justin Verlander or like Corbin Burns?
Sure, and I chose not to talk about, so the question is whether, most of this talk was about batted balls, but I could have easily talked about pitch balls too. It's just the choice that I made. Yeah, there's been a lot of studies by me and by many people on characteristics of pitch balls. So again, the StatCast data is an enormously useful tool for making such studies. So the Hawkeye cameras are really tracking the entire pitch. So you can measure the release point. You can measure where it crosses home plate. So in fact, when you look at the game on TV and they show you the little box there and they show you where the ball was relative to that box, which represents the strike zone, that's entirely from StatCast data, from the Hawkeye data. And they tell you the speed of the pitch, and usually they're telling you the speed at release. And again, that comes directly from StatCast data. If you get into more sophisticated analyses, they tell you the movement of the pitch, how much that pitch deviated from a straight line due either to gravity, which is always pulling it down, or to the fact that it's spinning. Maybe this is getting to your question. The spin rate, the movement of a pitch is directly related to the spin rate of the pitch. Okay, the faster it's spinning, the more movement you're going to get. So, for example, for a so-called four-seam fastball coming at you with backspin, the Magnus force is up, and so Jarrett Cole's pitching today. He has for the Yankees, he has a high spin rate, high speed four-seam fastball, and that keeps, because the Magnus force is up, opposing gravity, the ball doesn't drop as far. That ball is high in the zone where it becomes really kind of difficult to hit, and especially difficult to hit at some optimum launch angle. Top spin makes the ball fall. The curveballs have top spin, and the Magnus force is down, okay? So it goes in the same direction as gravity, and those pitches are low in the zone. And so, you know, I think pitchers and sliders have mostly side spin. So anyway, the movement is directly related to the amount of spin. The direction of the movement is related to the spin axis. You know, is it top spin, side spin, back spin? Now, last year, there was a bit of a controversy in Major League Baseball having to do with sticky stuff on the ball, okay? There was the sticky stuff controversy. And it was observed, because we have good measurements, that for many major league pitchers, the spin on, say, their four-seam fastball had actually gotten bigger by 10% maybe, something like that. And it was because of the sticky stuff. So what is the sticky stuff? You put sticky stuff on the ball, you hide it somewhere, and, all right, you put it on the ball, and it increases the friction between your fingers and the surface of the ball, which allows you to get greater spin on it, okay? And beginning in, was it June? Beginning of June of last year, MLB decided they had to do something about this. It was getting out of hand. And so they decided they announced that they were going to start inspecting pitchers to see whether they were putting sticky stuff on the ball. And it's remarkable, if you look at the StatCast data, you look beginning in, I think in June, and the spin rate on all kinds of pitches just dropped league-wide. So once MLB started enforcing things, then apparently the players, the penalties for using this, I don't remember what the penalties are, but they're severe enough that you don't want to get caught. But some pitches were affected more than others. I think Verlander may have been, there are several pitches were really, really relying on this to be able to, you know, get good spin on the ball. And it took them a while to adjust once they decided to stop that. But they did adjust, and they learned how to pitch without the sticky stuff. And maybe they're still cheating, I'm not sure. Did I answer your question? Is that the question? Yeah. Any other questions?
How would you calculate the optimum launch angle?
How do you calculate it?
Why is it 28?
Without air. So the question is, why is the optimum launch angle for greatest distance 28 degrees rather than 45 degrees, which is what it would be in a vacuum? It has to do with the air drag. So I'm gonna not try to explain it exactly why it is, but it's easier to measure it than to explain it, and you measure it, and there it is. And so this is a good example of how physicists proceed about things. So I have a trajectory, what I call a trajectory calculator. You could find it on my website, that allows you to plug in exit velocities, launch angles, and see what the ball does, okay? And that trajectory calculator has to put in information about the drag, and that information is maybe, you know, not so well known, and so you sort of adjust that to fit the data. Because you can't calculate it from first principles. It's simply the so-called drag coefficient. No one has yet been successful at calculating that from first principles. So you treat it as an empirical formula, okay? This is what Adair says: the physicist's model of the game must fit the game. And so when you put in drag coefficients that more or less reproduce pitch baseball data, you see that they also give you that something like 28 degrees. And you could go use that, you could try playing around with that yourself if you wanted to, changing angles and see what happens. Next question.
Hi. So in many ways, baseball is similar to other sports like cricket and other things, right? So how well you could translate your studies and your observation to other sports?
Yeah, so the question is how well do these studies translate to other sports? The physics is all the same. The details, of course, can be very, very different. So any sport where you're striking a ball involves basically the same physics, whether it's tennis or cricket or baseball. You know, how hard that ball is hit will depend on the same quantities. The quantities might be different. The speeds are different. The collision efficiency is different. Coefficient of restitution is different. But the physics is all the same. And so that's one of the things that physicists like to do is generalize things. So the theory is independent of which sport. The parameters that enter into the theory may change from one sport to another. Similarly with aerodynamics, the flight of a spherical ball, it's a little harder for American football, but the flight of a spherical ball through the air doesn't really depend on whether it's a baseball, a softball, a tennis ball, a cricket ball, pick another ball, ping pong ball. I mean, the drag coefficients might be different, the size might be different, the weight might be different, but the underlying physics would all be exactly the same.
Our last question, but Professor Nathan will also be available if you'd like to come down and ask a question in the front after this.
So, do you have time to talk about a hollow wooden bat from MLB?
A hollow wooden bat for MLB. Okay. I'll tell you another story. So in June of 2003, I think it was, I woke up to find that Sammy Sosa for the Cubs had corked his bat. Okay? So what is corking a bat? Corking a bat, when you do that, you're drilling a hole maybe an inch in diameter into the barrel of the bat, maybe about a foot deep, and then you're backfilling it with cork. And it's illegal, all right? And the cork plays no role other than to increase the weight from what it would be if it were hollow. The primary purpose of the cork is to hide the fact that you have done this, okay? So in effect, you've created a hollow bat, okay, by doing that. And the question is, I guess is your question, does this hollow bat have a trampoline effect? Is that your question? Okay, so I suspected that the answer is no, but we actually did an experiment. And the answer is no. So we had a bat, and you know, that same apparatus that I showed you, the way NCAA measures the BB core of a bat, we used that. We bounced the ball off an unmodified bat. Then we took the same bat down to the machine shop. You drilled a hole through it, bounced the ball off the bat again. Then we filled it with cork, did it again. And then we got the idea we'd fill it with lead and do it again. But we never got a chance to do that. The bat broke by the time that happened. But it was the same bat. And the ball-bat coefficient of restitution, which would be the indicator of whether you had a trampoline effect, was virtually the same for all those. So if you actually go to the paper that I referenced about the humidity measurements, it's actually discussed in that paper.
Very much.
I'd be happy to
Yes.
hang out here as long as, and if I think you're free to go, but if you want to come down and ask me more questions, I'd be happy to stay.
Yes.